Ruby is the work of Albert Rich, and he started working on it in 2008. Ruby is a rule-based system for finding optimal antiderivatives for large classes of mathematical expressions. There are around 7,000 integration rules right now. They are organized as a decision tree to find the antiderivative. There's a test suite that contains over 72,000 integration problems to test basically the system. And all this is open source and available on GitHub. Why don't we start with a simple example? So for the installation, you can call paclet install and give the online resource, or you could go to GitHub and download the paclet from there, or you could even clone the repository and use the latest development version. After that, you simply load the package as usual. Okay, and then Ruby just provides one function, which is called int for integrate. And essentially, it works very similar to what Mathematica has with its integrate function. So we can call it and we get the antiderivative of the expression that you see here. So, and then we could even compare it with the one that Mathematica gives, or we could give the bounds for the integration, right? You see, it kind of works similar. So what I do know is that integration is much harder than derivation, even if you do it on paper. And algorithmically, it's kind of similar. So you need very complex methods to integrate expressions that go beyond the simple things we probably see in school. One of these algorithms is, for instance, the Risch algorithm, which was a milestone in computer algebra as far as I know. And the thing is that these other algorithms usually give you an answer if they can calculate it, but they can't show you how you get to that point. So there's no way to follow the steps on paper, how you got the antiderivative of an expression. The other thing is that antiderivatives are not unique. So you can have many of them for a single expression. And the thing is that different antiderivatives can be drastically different in quality, both in size, but also in the quality of the functions that are used in the antiderivative. Ruby tries to solve specifically these points. So first, Ruby tries to give optimal antiderivatives in quality, but also in size of the antiderivative. We'll see an example in a moment. But the other thing is the nature of following a rule-based approach, applying rule after rule to get to the antiderivative, gives you a way to see how it was calculated, what transformations were used, and how you could repeat it on paper. Let me try to demonstrate what I mean by size of the antiderivative. We will use the very first example we've seen, but we will change the exponent to a 2023, which is more appropriate, I think. So when we integrate this with Ruby, we get a pretty short result. And to now look how big basically this is, we could use something like the tree form, and then we could count the leaves in there. And it's not entirely correct what leaf count gives, because it regards, I think, the rational expressions a bit differently. But leaf count gives a good impression of basically how complex or big an expression is. If we integrate that with Mathematica, we get a vastly different result. And it's so different that basically this leaf count here is orders of magnitudes bigger. But actually, it's still a valid antiderivative, and it's correct. And you can simply show that by doing the opposite operation. So you take the antiderivative and you derive it again and see if you come back to the original form. Let me give another example regarding the quality of the antiderivatives. What we use is a simple expression that contains a cosine in the denominator here. We will first integrate it with Ruby and then with Mathematica. What we will see is that the result looks pretty similar. So let's try to integrate that here and then that here. You see, the forms are not that different. If we simplify it back, we also see that we get to the original form. And the next step I want to do is I want to just plot basically the antiderivatives of the result of Ruby and the result of Mathematica. For the result of Ruby, we see that The original function is continuous in the region I plotted here, minus 2 pi to 2 pi. And the antiderivative is also continuous, which is a good thing. If we look, however, on Mathematica's solution, we see that there are discontinuities in the solution. Generally speaking, it's always nice if you have a continuous function. So, for instance, in the one with the discontinuities, we couldn't just simply plug in values to calculate the area under the curve. I have to say that Mathematica does a great job taking care of these discontinuities if you actually calculate the area in a region that goes over such a jump. So if you call integrate on that, you will get the correct answer. It's roughly 1.4 here. So with Ruby, however, we could just take the antiderivative and plug in the values left side, right side, and then subtract them from another. And what we get is the same result. And if I scroll down, we could not do the same with the antiderivative that Mathematica provided because it contains these jumps. The last thing I wanted to show you is how you can actually look on the steps that Ruby took to calculate an antiderivative. We have a helper function for that. It's called steps. You just wrap it around and Ruby will take care of collecting all the information from all the rules it applied. If we call it on this very simple expression x to the power of n, then we will get a view of what rules are applied. So what you see here is in slight red, basically the rule that was applied, and in blue, then the intermediate expression that was used to continue if there would be more steps. So in that case here, it's pretty simple. There's a rule for x to the power of m, and it looks like that. We can also expand that. And what we see here is that Ruby used the rule 30. However, what makes this approach so powerful is that in longer calculations, you can basically follow each step that was taken by Ruby. Right? Let me give you another example. So here we have a bit more complex expression. And if we integrate that and using the steps function, we see we get a much larger output. So obviously, the first rule is just that the integral of a sum of terms is basically integrating each term separately. And then we have these sub-expressions. And for each sub-expression, other rules were called so that finally the output is given at the bottom. It gives you a deep understanding of how to integrate something. You can look on the rule, you can look on the conditions of the rule, which is basically the requirements that need to be met so that the rule is applicable in a certain step. You can look on Albert's notes, and finally, you can just look on the code that implements the rule and see for yourself how it works. Now we have a pretty good impression of how Ruby looks from the user's perspective, but I'd also like to give you the other direction from the developer's point of view. Let's start by heading over to Mathematica and implement our own very simplistic Ruby. It will do nothing more than find the antiderivative of polynomial expressions like you see on the screen. So we will call our integrator just int. And the rule for integrating the terms here is simply that, okay, if we see an expression like x raised to the power m, and we want to integrate it with respect to x, then we get something like 1 over m plus 1 times x to the power of m plus 1. So that's the rule. We can test it already and say, okay, find us the antiderivative of x squared, and we get a result. So one thing you should see is that this goes south pretty fast if we don't have a 2 here, but instead a -1, because then the solution is something different, right? But we can add this rule. We can say, okay, if we have indeed 1 over x, and we want to integrate it with respect to x, then the result is log of x. So let's see. Good so far. Another thing that you might see is that we want to integrate just simple x because it's just raised to the power of 1. But in our current approach, this stays unevaluated. The reason is that Mathematica doesn't know that this is basically default to the power of 1. But we can add this by simply adding a point which adds the default argument. And then Mathematica knows that the x is raised to the power of 1 and we get the result. Okay, that looks pretty decent. However, there's another flaw in our approach. What if our power is not free of x? Then the rule doesn't work. This is exactly the case where we need conditions on the rule. So if we have something like x plus 1 here, our approach is wrong. So what we need to do is we need to put a condition on the rule. And here we can simply say something like free q mx, which says, okay, m needs to be free of any x's. So now it stays unevaluated. And of course, we need to think of another rule that we should add. The last point is that what if we have our example plus x? It stays unevaluated because how should our integrator know how to integrate a sum of terms? So that's where we need another rule. And we can say something if we want to integrate something that contains a plus and has arguments, and we want to integrate it with respect to x, then probably what we want to do is just integrate all the single parts. So we can say, yeah, just use our integrator and map it over all the arguments. So this will give a list, and what we finally want is make it a sum again. Okay, and there's another flaw here. So we need to prevent that this is evaluated when we define it. So we need to put a hold pattern around it. And what happens now is basically that our integrator sees first that it is a sum. So it uses this rule, right, to integrate the parts, and then each part is integrated separately. You might wonder why I'm talking about rules all the time. One way to think about that is that Mathematica also stores all the definitions you give in rules. They're called down values, or there are certain other types of values as well. But for our specific integrator, we can look at the rules. So what we can do is simply call down values for our int. And then we see the rules that Mathematica uses. So they have a left side that usually contains a very specific pattern that needs to match, right? And if it matches, then it's replaced with the right side. So another thing it has usually are these conditions on rules that we use extensively in Ruby. So even if a pattern matches, there are certain additional conditions that need to be met so that the rule can be applied.